All right, so real quick, a couple of things. Today what we're going to do is a full three-dimensional, finite element derivation of a bar or a beam element. Last time we did a bar element, and this time we're going to do a beam. A couple points I'll make. So last time what we did was what we call a two-noded bar element, which means you have a single bar element and you only have two nodes or two joints, whichever one you want to use. For your homework that I'm going to give you in the not too distant future, I'm going to give you a bar element, but it has three nodes. You're going to do that one on your own. Now, one thing I will say, and I'll just sort of be honest about it, there are some things that are unique to beam elements that you will not see in other elements. And they're mainly associated with the derivatives that we use. I will do my best to indicate the stuff that is unique to beams, but you'll want to make sure that you pay attention. Now today, it's not a, here's a handout and follow the slides. Today is we do it together, because I really feel there's only one way to really learn this methodology, this finite element approach, and that is to do it. Okay, so today we're going to do a finite element derivation of a beam element. Okay? All right? And maybe I'll have a drop the marker moment at the end. We'll see. Okay. So, real quick, a couple things. How many degrees of freedom does a bar element or a beam element have in total? A beam. How many degrees of freedom do we have? 4. Okay, we have a vertical translation at each joint, and then we have a rotation at each joint. Is that a fair statement? Okay. So here's what I want to get at. Let's look at the element and its displaced shape. Okay, so what we'll do is we'll say, all right, here's the element, and we have some joint or some node here, some joint here, whichever one you want to call it, and some joint on the other end. We'll say that this element has a length of L. Okay, all right. Now, I propose to you that this element can have a translation on each end and a rotation on each end. So what I might have is, first off, when it comes to the joints themselves, I can have, like its displaced one might be somewhere up like that, and over here might be something like that, where this dimension is, I'll call it V1, and this dimension, we'll call it V2. Right? But it's not just that. There's also its rotation at each end. Now, mathematically, if I'm talking about rotation, another way of expressing that might be to look at its slope. Is that a fair point? So, if I look at the displaced shape of this element, just in general, I'm not saying, always, just in general, it might look something like this. Maybe something like that, where, like if I'm looking at, joint 1, the one on the left, not only do we have a translation, but there is some angle of rotation, theta 1, which is essentially the slope, right? And then on the other end, we have an angle of rotation here, theta 2. Is that a fair point? Not too shabby. Maybe I can clean this up here on this end. Like that. And this. Theta 2. Something about like that. Fair point? So, if I wanted to write its vector of nodal displacements, the D vector, remember that's the vector of all those constants, I might say it's V1, theta 1, V2, theta 2. And those are the constants that define that displaced shape. Is that a fair point? Okay. Now, what we did with the bar element last time is we said, all right, all we have for the bar element are two unknown displacements. We have one here and one there, right? A U1 and a U2. We said, well, if I have two constants, two graphed constant values, and I want to find a value in between them, the easiest way to do that mathematically is linear interpolation. So we assumed that the displaced shape was linear, right? That's where we got that u equals c naught plus c1x, and then we use the boundary conditions to solve, right? Now I'm proposing that that function wouldn't make any sense for a beam, okay? So what I'm talking about is I'm saying this function right here. This is my displaced shape. That's v of x, okay? And that's really not going to work for us, assuming a linear function. I mean, is that a line? That doesn't look like a line to me, does it? That's not a straight line in any way, shape, or form. It's got some curve to it. So here's what I propose. I propose that for this beam element, I'll say therefore, our assumed, and I want you to get really familiar with that concept of an assumed displaced shape. That's where the finite element method starts to get approximate, this assumption. Our assumed displaced shape is going to be as follows. See, for the bar, we said that our displacement was c naught plus c1 times x. Now, let me ask you this. We had two unknown constants here, c naught and c1, right? And those corresponded to our two displacements. How many displacements do we have here? Or how many? 4. So I propose that we just keep going on. So we assume that our displaced shape is cubic in nature, which actually fits a lot of what you do with beam theory. If you all remember from structural analysis, if you look at beams, a lot of times you get that the deflection as a function of x has some x cubes in there. So it's not like that's completely an off-the-wall expression. Okay? Is everybody all right with that assumed displacement? Now, what I'm going to write next is going to be very unique for beam elements. Okay? Now, not only for beams, see, beams are unique because with beams, we don't just care about the displacement. If all we cared about was the displacement, this would still be a straight line. But with beams, not only do we care about the displacement, we care about the slope. Okay? So, instead of just using this shape function, we're going to need the derivative of that shape function. So maybe what I'll do is I'll put, so that you all have it, I'll say only for beams we're going to need to do this. We're going to need some displacement function as a function of x, and that's going to be taken as v prime. Take the derivative, right? So, you all had calculus. What is the derivative of this? Well, we take the derivative of c naught, which is, what's the derivative of a constant? What's the derivative of 4? 0. There we go. Plus c1 times x. What's the derivative of c1 times x? c1. There we go. c1 plus, you tell me what to write. c2 times 2x. So maybe 2c2 times x plus 3c3 x squared. There we go. Not too bad, right? Simple stuff. Okay. So far so good? Okay. Now, we need to know what those constants are, right? Now, in order to know what those constants are, we need boundary conditions, okay? Now, I propose to you that there are 4 boundary conditions for this problem. 4 unknown constants, 4 boundary conditions, okay? So, let's see if we can just start listing them right off the bat. Am I good to drag this down a bit? Okay, I'm going to keep this all on one big line, so I'll keep going up and down if you need me to. All right, so boundary conditions. First off, let's just list them. Let's see if we know what they are. So we've got 4 boundary conditions. I'll start us off with the first one. Can somebody tell me what this is going to be? V1. There you go. Exactly. We know that the displacement at x equals 0 better be V1, right? Okay, so let's do the next one. Theta at x equals 0 better be theta 1. So you tell me what to write for the next 2.
V1 at x equals L.
There you go. At x equals L is V2. And theta at x equals L is theta 2. That's not too bad, right? Simple stuff, right? Let's start evaluating each of these one by one. Sound good? Let's start off with the first one. Okay, so I'm going to drag this down a bit. So, number 1. So, I'm looking at the displacement at x equals 0, and that equals V1, right? So, here's my displacement function. So, what do? I plug in x equals 0, and I set it equal to V1, right? So, what do we have? So, we have that V1 has to equal C naught plus C1 times 0 plus C2 times 0 squared plus C3 times 0 cubed. Do you see what I did there? So, have I solved for one of my unknown arbitrary constants? I know what C naught is. So, therefore, C naught equals V1. There's one of them, right? I'll box that one. Kind of big. That's a good one, right? That's number 1. What about number 2? Now, number 2, we use the derivative function. So instead, I'm looking at this one down here, the C1 plus 2C2x plus 3C3x squared. And I set x equals 0, and I set the whole thing equal to theta 1, right? All right, so what do we have? We have theta 1, we set the whole thing equal to theta 1, equals C1 plus 2C2 times 0 plus 3C3 0 squared. So therefore, C1 equals theta 1, right? So far, so good? This is easy so far, right? Now, it's not bad. It just, I'll say, from here on out, I should just mention this, this problem for a little while will feel a little bit like alphabet soup, just a lot of algebra, and a lot of calculus, a lot of variables. But in the end, when it's all said and done, you will see a point to what I'm doing. I promise. Okay? And again, it's so that you understand the finite element method process for deriving an element. Okay? Everybody good so far? Okay, so let's do number 3. Okay, now number 3 is going to be a little different. But before I do, let me do this. Let me rewrite my functions. Oh. Let me rewrite them a little bit. So what was v of x? It's c naught plus c1 times x plus c2 times x squared plus c3. We've already got c naught and c1 there, right? So I'm going to say v1 plus theta 1 times x plus c2 x squared plus c3 x cubed, and theta of x is c1 theta 1 plus 2c2 times x plus 3c3x squared. Okay, is everybody good with this? Okay, all right. So now I'm going to do 3 and 4. All right, so let's do number 3. All right. All right, so the whole thing's got to be set equal to V2. And what do we have? We have V1 plus theta 1 times what? L. We're plugging in L. Plus C2 times L squared plus C3 times L cubed. Is that a fair statement? So could I rewrite that as follows? Could I say that C2 L squared plus C3 times L, do better than that, L cubed equals what? V2 minus V1 minus theta 1 times L. Would that be a fair statement? Now, I'm going to box this in, but this by itself really doesn't do much for us. Okay? Doesn't really do much. You'll see why here in a second. Let's do the next one. Let me drag that over a little bit. Let's do number 4. So number 4, I'm dealing with the bottom equation. The whole thing's got to equal theta 2. So that's theta 1 plus 2 C2 times L plus 3C3 times L squared, right? So if I rewrite that a little bit, I've got C2 times 2L plus C3 times 3L squared equals theta 2 minus theta 1. Give you all a second to catch up, writing all that down, what have you. All right. So far, so good. How you see where I'm going with this? Everybody good? Okay. Now, what we're after in this are these constants. That's the whole point of what we're doing right now. We're trying to solve for these arbitrary constants. So, C2 and C3, if I look at these two expressions, I have, in fact, 2 equations, and I have, in fact, 2 unknowns. The entire purpose of this class involves matrix algebra. That's what we're doing in here. So we better be able to handle something like this, okay? So we'll take our time with this and see how this works, okay? Is everybody good so far? Okay. Now, what I'm going to do is I'm going to take these blue boxes and I'm going to write them in matrix form. Okay. So in matrix form, what do we have? Okay. We've got, and I'm going to write it down, and then we'll take our time and explain it. I have L squared, L cubed, 2L, 3L squared, C2, C3 equals that expression there, and theta 2 minus theta 1. Now, if you're still a little iffy, okay, just walk it out, okay? Take the first row. This times this plus this times this. Same thing up here. Equals that. Bottom row. This times this plus this times this equals that. This is just taking that expression and rewriting it. You have a chance to write this down. Everybody good? Okay. Now, I know that you all have done problems like this before. Okay? So, I'm going to bring it back. Okay? How do we solve a 2 by 2 system? We take the inverse of this and multiply it over there, right? Y'all remember that? Okay, so let's see if you all remember this. If I recall, recall. Probably did this in high school or freshman year or what have you. If I have a matrix that's like A, B, C, D, and I want to take the inverse of that matrix, what do? Well, on the outside I've got a fraction, right? And it's an AD minus BC is the determinant. Right? And then I multiply that times the matrix. And what do? Along the main diagonal I swap them, so I got D and A, and then these I change the sign, right? You were on that. There you go. Alright. Y'all remember this? I know it's been a while, but I know you've done this before, right? Okay. So this is, right now, we're just in that whole algebra grunt mode to try and get all this stuff worked out. Okay, so I'll put therefore. Let's do the AD minus BC component. AD minus BC. How are we going to do that? Well, it's going to be L squared times 3L squared, right? Minus L cubed 2L, right? So what is that? L to the 4th. There you go. Alright. So far so good? So, therefore our inverse is, what do? We have 1 over L to the 4th times what? So we swap the main diagonal, so we'll have 3L squared and then L squared, and then change these signs. Fair statement? Now, just to simplify everything, because I like, reducing the symbology as much as I can, could I factor something out of this matrix? Does everybody see a common term? An L. There's an L in everything, right? So if I take L and bring it out, L over L to the 4th, that's just 1 over L cubed, right? So just to keep everything kind of simple, I'll say 1 over L cubed, and then we've got 3L minus L squared minus 2 and L. Just less exponents, less stuff to write. You know how it goes. Make sense? Alright. So far so good? Give y'all a moment to catch up and write all that down. Everybody good? Okay, now, so I need to take this inverse matrix and multiply it times that, don't I? So if I want to solve for C2 and C3, I take what? The 1 over L cubed, 3L minus L squared minus 2L, and I multiply it by that, right? Oh. Okay. Does that make sense? Sound good? Okay, all right. Now, here's where things get a little messy, right? Because I've got to do this matrix multiplication, right? So what do I have to do? I have to take 3L times this whole quantity plus negative L squared times this whole quantity, right? So there's a lot of, it's almost like FOIL. You got to carry it all out, So you all have a bachelor's degree in engineering, so I've got to believe you can do algebra, right? So you've got to have the skills to multiply all this out. My point is, would it be all right if I just gave you the end result of all that multiplication? Is that all right? Okay, all right. I propose to you that you do all this out, you carry all this out, and you're going to get this. What do we have? We've got 3v2 over L squared minus 3v1 over L squared minus 2 theta 1 divided by L minus theta 2 over L. Now on the bottom, 2v1 over L cubed minus 2v2 over L cubed. Be better than that. Then plus theta 1 over L squared plus theta 2 over L squared. I know that's long. But what I'm saying is, take 3L times this minus L squared times this, take minus 2 times this, L times that, multiply it all out, then divide everything by L cubed, simplify, do all the collection, and that's what you're going to get. I know it's messy, but in the end, that's the answer. All right? Are you all right with that, or do you want me to carry it out? You good? Okay. All right. Okay. So, all right, let me give you all a moment because y'all are still writing. Okay. So far, so good. Does everybody have all this written down? Okay, all right. Now, okay, so, therefore, let's go back to the very beginning of what we were trying to do. V of x equals C naught plus C1 times x plus C2 times x squared plus C3 times x cubed. Right? Okay, now, C naught was what? That was V1 plus theta 1 times x plus 3v2 over L squared. See where I'm going with this? Oh. Yeah, there is no theta 2 there. Or 2 times the theta 2. Okay, give you all a moment. Beams that we're talking about, I'm giving you a moment. I've said that like 4 or 5 times and nobody. What's that?
It's a lesson learned.
Okay. All right. We're going to try and make this now make a little more sense. Okay? Now, recall what we did with the bar element. I know that this has been a little long and there's a lot of alphabet soup, but I really want to make sure we're understanding the big picture. So we assume a displaced shape, and that displaced shape is based off of V1, theta 1, V2, theta 2, which we assume that we know. Like we know theta, if we know V1, V2, theta 1, theta 2, we can solve for displacements anywhere else. So what I want to do is factor out the V1s, factor out the theta 1s, factor out the V2s, factor out the theta 2s. Fair statement? So watch what I'm going to do. All right? I'll try and use a little bit of color with this. Let's start off with the V1s. Let's see everywhere we see a V1. I see a V1 right here, see one right here, see one right here. Okay? So watch this. What is V1 multiplied by on this first term?
1.
1. Okay? What is V1 multiplied by on the second term?
Minus 3.
There you go. That's right. Minus 3x squared over L squared. Because there's still that x squared on the outside, right? Everybody see that? Because you got 3 over L squared negative and then times x squared. Everybody all right with that? Plus, what's going to be over here?
2x cubed.
There we go. 2x cubed over L cubed times V1. Is that a fair statement? Plus, now let's do theta 1, because that was the order. V1, theta 1, V2, theta 2. So, what do we have theta 1? We got this one, we got this one, and we got this one, right? So what do we have? We've got x, we've got
minus 2x squared.
this one, x cubed, okay. Now V2, we got this one, we got this one. That's it, right? So we've got, what is it, 3x squared over L squared, and then minus 2x cubed over L cubed times V2. And then if it's all right, I'm going to put this one down here. And then it's only the ones that are left. So minus x squared over L, and then plus x cubed over L squared, theta 2. Is that a fair statement? Let me check and make sure I didn't make any mistakes. Looking good so far. All right. Give you all a minute. I didn't say moment that time. We've had enough moments in here. Center that up a little bit. Now, if you've been following along with what's going on, these terms on this last row, the terms in these parentheses, what do you think those are? That's our N matrix, isn't it? What was our N matrix last time? It was like 1 minus x over L and x over L. But remember, how did we get it? It was a pile of junk times U1 plus a pile of junk times U2, right? Look at what we have. A pile of junk times V1, a pile of junk times theta 1, a pile of junk times V2, a pile of junk times theta 2. Right? Make sense? Okay. All right. I'm going to extend this a little bit if that's all right. So I propose to you that my N matrix is going to be, what, N1, N2, N3, N4, and what do we have? We have that N1 is, what is it? It's 1 minus 3x squared over L squared. We have 2x cubed over L cubed. We've got, here I'll put N2 over here. Group those like that. So N2, that's where we have X. Oh, okay, I see, hold on. There we go. So I propose to you that what's inside this right here those are the shape functions that we've been talking about. I know it's a little laborious. The algebra is pretty heavy. If it makes you feel any better, that's actually less algebra than what you're going to do on your homework. It's less algebra than your homework. What do you think? It's not bad, right? Okay. So far, so good? Now, before I go into doing a B matrix, we got to do something a little bit different for beams. Okay? So, what I might do is I might extend this a little bit and have a discussion about beam mechanics a little bit because the math is a little different. Okay? Everybody all right where we're at so far? Okay, all right. So let's do a mechanics discussion. And before I do that, I'm going to put another one of them little stars and say only, or getting ahead of myself, only for beams. Okay. Let me just ask a fundamental question. If I want to calculate the bending stress in a beam, how do I calculate the bending stress in a beam? This is one of the most fundamental formulas that you learn in mechanics and materials, mechanics of deformable bodies, strength of materials. What's that? Well, no, it wouldn't be P over A. We're not talking about a bar. We're talking about a beam. Y'all remember that, right? And Y over I. You should have at least seen it somewhere. Okay? Some of y'all had me for concrete design. I know we used it in there.
That's the first time I saw it.
What's that?
That's the first time I saw it.
Oh, goodness. All right. So, sigma equals my over I. So, could I just, from a simplified standpoint, how do we calculate strain? We take stress and divide it by E, right? So could I say, therefore, that strain is M over EI times Y? Would that be a fair statement? Everybody okay with that? So, now, if you've had a class in structural analysis, or if you've paid attention at all at what we've been doing before, M over EI, that is a very, very popular term in beam mechanics, and we say that M over EI is the second derivative of deflections. Y'all remember that? Remember the Euler-Bernoulli beam bending expression? That the second derivative of deflection. You probably saw it as y when you took it in structural analysis, is m over EI. That's how you do double integration. That's the first beam bending formula that you learn. You take your moment function, you integrate it twice, you do boundary conditions, and then you get your beam deflection. I know you've done it before. It might have been a while, but I know you have. All right? So, is that a fair statement? So, here's what I propose to you, and this is what's different with beams than with bars. Okay? With bars, what did we do? With bars, so maybe I should make sure that we're really indicative of this. Okay? Therefore, for bars, we had that the strain, was the B matrix times the displacements, right? Or B1, B2, U1, and U2. And does anybody remember for bars, how did we get the B values? We didn't integrate, we took the derivative. But here's the thing. I'll say where BI, like one of those terms, was the derivative with respect to x of Ni. And we just took the derivative once, right? For beams, I'm going to say the following. I'm not changing my definition at all of this. Okay? I ain't changing that at all. But what I am saying is this. First off, I'm going to have, what is it? B1, B2, B3, B4. Then I'm going to have V1, theta 1, V2, theta 2. Right? Is that a fair statement? Then I'm also going to have that little Y sticking out there. And I'll circle that. Or highlight that, underline that very descriptively. So, look at this. See how for bars I have B1, B2, and that times that, but for beams I've got that little Y sticking out there? Everybody see that? That is important. Okay? Now, another thing that's important, for bars, I took the first derivative. What am I going to do for beams? The second derivative. There we go. So what I'm going to do is I'm going to say where BI is Ni. So maybe what I ought to do is I ought to say, okay, this is what we did for bars, but for beams. Look, I'm trying to color in between the lines again. When I was a kid. All right. Does everybody understand the difference? Why are we taking the second derivative for beams than we are for bars? Because it's a different problem. We're talking about beam bending. Okay? So I put this thing like only for beams. What I was talking about was this. I was talking about that. How we take the second derivative and how there's a y at the end. Everybody okay with that? Now, if you're all right with that, we'll get back to grunting away at this a little bit. So far, so good? Okay, all right. Can I extend this page a little bit? Now, let's only do the first one, because I'm not going to make y'all take a bunch of derivatives over and over again. That gets kind of silly. So, N1 equals what? 1 plus, what was this? 2x cubed over L cubed, sorry, it's L cubed. And then, what was that?
Minus 3x squared over x.
there we go, minus 3x squared over L squared. So what I'm going to do is I'm going to say, all right, I need to take the second derivative, right? So what's the first step in taking the second derivative? We take the first derivative. So what do we have? We have n1 prime is, okay, what do we have? We have the derivative of 1, which is 0, plus, and then what do we have? We have 6x squared over L cubed minus 6x over L squared, right? And then n1 double prime is, what do we have? So the 0 we can ignore. 6x squared, that's what, 12x over L cubed.
6 squared.
Everybody all right with that? So far, so good? Okay, now, so this is B1, right? This right here, like if I circle this, that's B1. Sound good? All right. Would you just believe me if I gave you the rest of it? You believe me? You trust me that much? I wouldn't lie to you? All right. Okay. So I'll say, oh goodness. B1 equals, B2 equals, B3 equals, B4 equals. Okay, let me write this out. So we have 12x over L cubed minus 6 over L squared. We've got, this one ends up being 6x over L squared minus 4 over L. All right. Next one, 6 over L squared minus 12x over L cubed. Last one, 6x over L squared minus 2 over L. And then remember, the B matrix is Y times B1, B2, B3, B4. So what I'll do is I'll do another big circle. And that's our gradient matrix. Give you all a moment.
Why is it increments that we go along with the beam?
No, that's a good question. No. Why? Okay, that's a good question. So, so the question was, what's Y? Okay, so here's my beam. Okay, X is along the beam. That's X. Y is actually vertical. Okay. The reason why, no pun intended, is if I go back to look at a stress vector, like what does bending stress look like? It looks something like that. And then we measure that stress from the centroid and we say Y is that distance. That's a great question. What is Y? It is from the centroid measured up or down. Because remember, bending stress gets larger from the centroid. And it's the distance Y. That's a great question. All right, does everybody, all right, I see some folks still writing all this down. We're doing pretty good on time, actually. We'll knock this out. And I have a surprise for you after class today, so. Well, you'll like it. No, it's not homework, you'll like it. All right, I'll go ahead and tell you the surprise since you've made it so far into this. I have to travel next week to Raleigh, North Carolina to do a presentation at the Steel Bridge Forum, so we are not going to have class on Tuesday. Is that all right? Everybody okay with that? You don't seem too sad about it, which is kind of hurting my feelings a little bit. All right. Is everybody okay so far? Okay. All right. I want to continue this out a little bit. Okay. First off, do you mind if I take a break from the screen capture for a second, because I want to look at something. Before I do, look at these B functions. Take a look at them. What do we have? We have 12 over L cubed, 6 over L squared, 4 over L, 2 over L. Y'all see these numbers? Watch this. Let's go back to this. Okay. Remember our original discussion of the beam element? We said we had translation and rotation. But instead of this approximate approach, we took a direct approach, right? Now, after that direct approach, we got this, right? What do you see? 12 over L cubed, 6 over L squared, negative 6, 2 over L, 4 over L. Starting to see where this is coming from? Am I all right with this? Okay. Now, there's a reason why I bring this up. Go back to the notebook. Okay. Everybody got all that written down? Okay. Okay, remember what we're trying to do is our stiffness matrix. Okay, so what is our finite element formulation of a stiffness matrix? It's the integral over the volume of B transpose times C times B dV. Over the volume, right? Make sense? Okay, now, a couple things I want to point out. Okay? So, keep in mind, we are still dealing with a single stress multiplied, or a single stress equals a single strain times Young's modulus, right? So because of that, I propose that our C matrix is still E, right? It's still like what we did with the bar. Remember how we said, technically you have a C matrix, but really it's just E, right? Everybody okay with that? Okay, now, so I propose we can take this stiffness matrix formulation and pull that out, and we just have, we have the triple integral over the volume, and maybe I should write my matrix brackets out. I have B transpose times B. Is that a fair statement? So far, so good. Okay, now, okay. Everybody all right with this? Now, I want to look at what's inside here, this B transpose times B. Okay? Would you agree that if I go over here on the side and just take a look at this, B transpose times B. Well, B is Y times that what? B1, B2, B3, B4? So what do I have? I've got Y times B transpose times Y times B transpose, or B. So really what I have is y squared times that. Everybody good? Okay, now, how do I take this matrix and multiply it by that? What's the resulting size going to be? 4 by 4, right? Because what do? I take this one on the left, take this one up top, right? So what does that look like? Well, what do I have? If I put B1, B2, B3, B4, and then B1, B2, maybe I should group those a little closer together. B2, B3, B4. Then I look at my answer. What do I have? Well, I've got, oh goodness. What do I have? Like I have what? B1 squared, B1, B2, B1, B3, etc., right? Then I might have what? B2, B1, B2 squared. Y'all see how I'm doing that? And I'll say, and so on, right? So, can somebody tell me, without doing any of the algebra or anything like that, what is this B transpose times B? What property is this matrix going to have?
Symmetric.
It's symmetric. Because B2, B1 equals B1, B2. And the same thing's going to happen across the board. It's symmetric, right? Everybody okay with this? Now, my last thing I want to look at is this right here. The y squared. Before, what we did was this. I'll say also, for bars, we did something like this. Remember how we had a triple integral and we said if something's constant over an area, you can pull that out? So we had this term, and we said that that was A, or the area. Remember that? Well, here we're going to have something a little different. I'll say for beams, get ahead of myself. We're not going to have the double integral of just one. We're going to have the double integral of y squared. Because we got that y squared left over, right? Okay? And this term y, the double integral of y squared over dA, we have a very special name for that in the world of mechanics, and we call it I because it stands for the moment of inertia. Everybody okay with this? I propose to you that the stiffness matrix for a beam will be as follows. So this is my be-all, end-all. Therefore, the stiffness matrix for a beam will be, converting that volume integral into an integral over the length, it will be E times I times the integral from x equals 0 to x equals L of B transpose, or I'll say, yeah, we'll just do that, B transpose, whoop, times B dx. And I guess I should put, to be clear, the B that I'm talking about is just the B1, B2, B3, B4, without the Y. So I guess I should put no Y term. Everybody okay with this? Let's test it out. And I'm not going to do every single damn term in the stiffness matrix, but I'm only going to do like one, for instance. Okay? Now, let's take the very first term, first column, first row. Okay? So what do? I take B1 times B1 and I square it, right? Everybody okay with this? So let me also put stiffness measure. Are y'all still writing? Do you need a minute? Okay, all right. Let's say, for example, K11. So B1, if we go back to our definition, B1 was what? 12x over L cubed minus 6 over L squared, right? So, therefore, how do we calculate B1 squared, right? We've got to do a little bit of, what do we call it, foiling? Remember that? Front, outside, inside last. So we have so what do we have? The first times the first is 144x squared over L to the 6th, right? Then we have minus, outside is going to be 72 times x over L to the 5th, right? Did I do that right? Minus 72x over L to the 5th plus 36 over L to the 4th, right? Did I do that right? Okay. So that equals 144 x squared. Here, I'm going to extend that. Everybody okay with this? So I'm then going to take this term and integrate it from 0 to L. Okay? So, therefore, if I want to get that first term in the stiffness matrix, I would do that, right? Everybody okay? All right. So, all right. 144 divided by 3. I don't think that goes in evenly, does it? No, yeah, it does. 144 divided by 3, that's 48. 48, right? So 48 x cubed over L to the 6, right? Minus 144, that's x squared over 2, that's 72 x squared over L to the 5th, minus 36x over L to the 4th. And that is from x equals 0 to x equals L. Is that right? I didn't screw anything up there, did I? So far, so good. So if I plug in the top number minus plug in the bottom number, right? What's the bottom number going to give me? 0, 0, 0. Ain't going to do anything, right? So the top number, what do I have? I have EIO. I'm just kidding. All right. So 48 times L cubed over L to the 6, that's 48 over L cubed, minus 72 over L cubed, minus 36. Oh, something's wrong with my signs. That's supposed to be a plus. 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 Over L cubed. Y'all let me get away with that. Yeah, this term here I'll circle it on the screen. I had that originally as a minus, so it's supposed to be a plus. So, what do we have? We have 48 minus 72 plus 36. That's 12. I think I'm in store. Nothing. Nothing. Goodness. Did a marker drop and nobody did. But my point is, do y'all see how we did that? Okay, so don't worry, I'm not going to do that for every element in the system. Let me hit escape. But that first element, or that first term in the stiffness matrix came out to be 12 EI over L cubed. If you do that for every one in the system, you'll get this. Okay, and that's it. That's all there is to it. Okay, that's the finite element method. Now we're running out of time, so next time I think what we might do is review this, but then we might ask, can we use the finite element method to get the load vectors as well? Y'all know those little fixed in force tables that I gave you? Can we use the finite element method to generate those? And the answer is yes, you can. Okay? Just so you all have a little bit of a taste of things to come, okay? The next question that we have to answer is, this is all nice and everything. Let me scroll down here a little bit. This is all nice and everything, but the one thing that these can't do is integrate. They're not meant to do integrals. They add, subtract, multiply, and divide. So how do we integrate with a computer? Or at least integrate effectively in a finite element standpoint. And we'll talk about a technique called Gaussian quadrature, where we can derive these elements numerically. And it's how software, higher level FEA software works anyways. That's all I have for today. I will see you all next Thursday. Okay, so Tuesday, class is canceled. All right. Y'all have a great weekend. And Thursday, the exam's due. One final thing, if you all need me, I should be available by email. So email me if you have any questions. All right, that's all I got.